Hey guys, today we are going to talk about vectors in R2 and R3. So, first thing here is we're going to talk about vectors in R, or in other words, one-dimensional vectors. So, a one-dimensional vector has magnitude, just like normal. So, has magnitude. The direction, which it has to have direction to be a vector, but the direction is just either going to be positive or negative because there's only one dimension, so it can either go one way or the other, and that's it. So, and either positive or negative direction. Okay, so you can look, you would just draw it on a number line, and you start at 0, and we just say, oh, there we go. So there's it's got a magnitude of 3, although I missed a little, and a positive direction. Okay, I could alternatively have one that's a magnitude of magnitude of 2, and a direction that's negative. So there you go. So if you were going to draw this, if you were going to write it as a position vector, okay, it has its tail at 0. Keep in mind we don't have to say 0, 0 because we're only dealing in one dimension, and its head would be at P. Okay. Before we get into any more, it is worth noting that R, when we talk about R, this is just all real numbers. All real numbers, okay, which you should have talked about in previous courses, but that's why we call it R1, R2, R3, is because each of these dimensions can have any real number as their magnitude. Okay, so vectors in R2, so these are two-dimensional vectors, so these would be defined by x and y. Okay, defined by x and y. Okay? So in other words, they're two dimensions. Okay. So you would write, so the pair, well, we'll jump over to the diagram in a second. I guess you can see it on your paper probably, but the pair V, whoops, that's not a V, Vx and Vy. So if we'll write it as an order pair, and these are the components of or represent the components of the vector. Or the scalar components, I suppose, because we write those as scalars, the scalar components. Components of the 2D vector. Okay. So and you can see that here if we zoom out. Where is it? There it is. So there's our diagram. You can see we've made up this vector using this Vx and Vy. Those are the components that build this vector. Okay. So it has its tail. So when we write this, when we're writing it as a position vector, it has its tail now at 0, 0, because we're in two dimensions, and then its head at point P still, but point P is made up of x and y. Okay. So, when we're dealing with vectors, we often talk about unit vectors. So there's two unit vectors in R2. Okay. We call them I and j. So the two unit vectors which are I which is equal to 1, 0. And then we have, oops, I guess I can write, and j, which is equal to 0, 1. Okay, I guess we should write these over here. Okay, these are called standard unit vectors in 2D. Are called standard unit vectors. In 2D. Okay. And you'll notice that they have a magnitude of 1, okay, which is why they're called unit vectors. So their magnitude is exactly 1 unit. All right. So vector components for 2D. So any vector v may be decomposed in 2 perpendicular vector components. So what we're going to say is, so yeah, and so what this means is that we can build any vector out of, so we'll call it Vx, okay, and Vy. Okay, so these are parallel to the unit vectors. Okay, and so in other words, the significance of this is that if we take any 2 vectors that are multiples of the unit vectors, we can build any vector in 2D. So any vector in 2D can just be made up, and you can see this over here in this diagram here. So we've taken this vector here, okay, vector v, okay, and we've built it out of Vy and Vx, which are just multiples of the 2 unit vectors. So this one, Vx is like 3 of the i's and 2 j's. So if we add 3 i's and 3 j's, it'll build us this vector. Okay, and this is true for any vector in 2D. We can build it out of these 2 unit vectors. Okay, so in other words, what we can do is, so the vector v is equal to the 2 component vectors Vx and Vy, okay, but what's more, what we can do is we can say, well, if we take the magnitude of Vx, whoops, so that's just the magnitude, so that's not the vector, and we multiply that by I, which is a vector, the unit vector, and we can add the magnitude of Vy times j, and this will give us the vector Vx, Vy. I'm sort of running out of room here. Oh, I keep doing that. Okay, and that will give us that vector. Okay, so we can build any of these vectors like that. All right, so that's what that's about. Let's see. So position 2D vector, the directed line segment OP from the origin to O to a generic point P, X, Y. So this point, so this vector OP, okay, which we can write as either X, Y as a vector, or we can say that it's X times, whoops, okay, it's xi plus yj, and these just become different ways to write vectors. It's just different notations, basically, and we use them for different things. Sometimes one's more useful, and sometimes the other's more useful. So, for instance, if I've got a point, I'm finding an algebraic position vector OA, where A is at -2, -3. Well, OA, the vector, is just at -2, -3, or I can write it as 2i plus, oh no, I guess that'd be a minus 3j. Okay, And that's it. So, and the idea is that then we can do computations using, so even though this guy right here is sort of more useful, more intuitive and easier to, think about what it looks like, this one right here is the one that we're going to end up using for computations and such, just because it's easy to work with. Okay. So, the displacement 2D vector, a directed line segment AB from the point A, which is XA, YA, to the point B, which is XB, YB. So then, I don't know what it says and. I feel like my grammar's wrong there. It doesn't matter. So, in other words, I can create a vector here by saying, well, if I take XB and subtract XA, that's a minus. And then I have YB minus YA. Okay, that'll give me the vector, but then what's more, I could write that as XB minus XA times I plus YB minus YA times J. Okay. So you get the idea there. So this one here, Mn. So basically Mn can be written as either -2, 3, because I subtract 0 minus 2, and then 2 minus -1. Or I could write that as 2I plus 3J. Okay. So that's that. So, I know what you're thinking. You're thinking this two-dimensional stuff is boring. Let's do 3 dimensions. So, first of all, vectors in R3. So we're going to, this is in 3 dimensions, which are defined by X, Y, and Z. Okay? So what you'll notice when we graph these, sometimes people get a little confused. You'll notice that the letters aren't where you necessarily are used to them. It took me a long time to get used to be honest. And the Y is the one that's sort of where the X used to be, and the Z's where the Y used to be, and then the X is the one sticking out of the page towards you. Okay, so keep an eye on that. It's an easy mistake to make just because you're kind of used to drawing the X and Y, in their normal location, sort of. But when we're drawing things in 3 dimension, the X comes out of the page. Okay. So if we're doing a position vector, it's fairly straightforward. We're just adding a new dimension. So we've just got it at 0, 0, 0, and then the head is at X, Y, Z. Okay. So, right-handed coordinate system, yeah, and this is supposed to be a way that you can, I can honestly say I've never used this and had this helpful, but a lot of people do. So it's just that by using your right hand, if you stick your fingers out, you're supposed to remember that your index finger is X and your thumb is Z and your middle finger is Y for some reason. I don't really know how that helps, but the bottom line is you just draw this guy, that's Y, that's X, that's Z. Okay? Alright, so sorry, I had to pause there and I kind of lost my train of thought. But so there are unit vectors in R3, of course, just like there are in R2. And not surprisingly, the first two are both I and J, but then we also have K. So I, that looks more like a J. Let's try that again. I is just along the x-axis, so it's 1, 0, 0. And then J is still along the y-axis, so it's 0, 1, 0. And then we've got K, which is 0, 0, 1. on the z-axis. So these are just the standard unit vectors in R3. Standard unit vectors in R3. Okay. So, and not surprisingly, we don't need to get into this right now, but just like in R2, you can build any vector in R3 out of these three vectors. These three vectors, these three unit vectors, by multiplying them and adding them, you can build any other vector. Okay, and so that's why they're important. So obviously this is going to be a bit of a challenge, but if I'm going to draw a vector OA, where A is 2, 5, and 3, don't forget that we are, of course, on the x-axis here, so the 2 will be about there, and then 5, so 1, 2, 3, 4, 5, and then we'll have 3 on the z, so 1, 2, 3. So how do you draw that? Well, you know, do your best. Sure, to draw a box like this can help. And like that, and then we can build it up like that, and then we can draw our vector from that point to that point, and there we go. So it's a bit of a challenge drawing in 3 dimensions, obviously, because we're drawing on a 2-dimensional plane, but do your best. I'm not going to do example 5. I'll let you do that on your own. And until next time, go Sabres.